Good morning. So this is our 19th session of the course Fluid Mechanics. So in the yesterday's lecture we discussed about the Reynolds transport theorem and then we saw its application for conservation of mass and conservation of the linear momentum principle. Okay. So we will try to see the linear momentum one in more details. So as I told you that the definition of linear momentum is m into v. Okay. So for this case, if I write in vector form, then I will be writing m into v vector. Okay. So now we can see from here that our b is nothing but equal to m into v vector, and beta, which is the intensive property per unit mass, that comes out to be v vector over here. Okay. So now if I apply the Reynolds transport theorem to this property, then what I will be getting that d by dt of m into v vector of the system, that will become equal to integral over the control volume del by del t, because I am considering that I have a fixed control volume. Okay, so for a fixed control volume it will be becoming v vector rho times dv bar. Okay, plus I will be having control surface over here, so surface integral, and then I will be having v vector, and then I will be having actually rho and v vector dot n cap into dv. Okay, and as we know that the rate of change of momentum of the system is nothing but equal to net force acting on the system, so this must be equal to f vector. Okay, now when we are talking about this equation, so there are few things which we need to understand. Okay, the very first thing is, whenever we are talking about the vector v, so v vector is actually measured with reference to inertial frame of reference. Okay, so this is with reference to inertial frame of reference, because if I consider the non-inertial frame of reference, then my fundamental law will be actually changing. Then it will not be only f equal to ma, but it will be having some other component as well. This point is clear. So when I am talking about the velocity vector, I am saying that it is measured with reference to the inertial frame. Because if I measure velocity with reference to the non-inertial frame, then my fundamental law f equal to ma will also change. It will be having some additional term also. What it will be, that I will talk about in the subsequent. Okay. So first point is that it must be in inertial frame of reference. Then second point is f vector is nothing but vector sum of all the forces. Vector sum of all the forces. For example, we have seen that if we are having a fluid element, then on a fluid element there can be pressure force, there can be viscous force, there can be body force if it is present in the gravitational field. If it is in the presence of electric and magnetic fields, then there can be electromagnetic force. Okay. So what I am trying to say over here, that whatever f vector I am considering, this is nothing but the vector sum of all the forces which are acting on the system. Okay, so these 2 points must be very clear to you when you are talking about this particular equation, because if you don't consider the vector sum of the forces, if you randomly select any individual force or a group of forces but not all, then this formulation will be wrong. Okay, so this must include all the forces which are acting on the body, on the fluid element. Fine. So now this particular equation can have other variants also. Third important point of this equation is that, is this equation a scalar equation or a vector equation? So this is nothing but a vector equation. So how we can see, if you see the right hand side, so it's a f vector, already a vector. If you see the left hand side, so this particular term, so in this term if you see v dot n will be becoming a scalar, but then I am having, so this rho v a, this entire is a scalar, but then I am having this v vector also multiplied over here. So overall this quantity will be nothing but a vector quantity. Similarly, if I talk about the first term, so here rho dv bar is nothing but a scalar. Rho dv bar is a scalar. Now it is getting multiplied with v vector, so it is also a vector quantity. Okay, so it means that this particular vector equation can be written in individual component form also. Okay, so if I consider that my v vector is nothing but ui cap plus vj cap plus wk cap. Okay, then ultimately what I will be having, I can write my x component of the force as nothing but equal to, now whenever I will be writing the x component, then ultimately all the terms of the equation must become scalar, because I am talking about a particular component which is a scalar. Okay, so fx will be becoming integral over the control volume del by del t, and in place of v vector now I must consider the x component of the velocity. Okay, so x component of the velocity will be u times rho into dv. Okay, similarly for the control surface, this term rho v vector dot n cap into dA, this will remain as it is, because this term is nothing but signifying the mass flow rate. This term signifies the mass flow rate. When I am talking about the x component of this equation, then ultimately I will be considering the x momentum or momentum in x direction. So this mass flow rate I must multiply with u component of the velocity. Okay, so now this particular is nothing but the x component of the force, and this is nothing but deduced from the main generic vector equation. Okay, is this one clear? Only thing is, whatever the quantities which we are considering, these quantities we are considering only in the x direction. Okay, now let's come once again to more simplified situation. Now if I consider that if I have finite number of inlets and outlets, plus I am also making one more assumption that all these finite number of inlets and outlets are with actually one dimensional fluid. Okay, so one important point over here, when I have written this component of the force in x direction, similarly you can write the components of the forces in y and z direction. The only thing in place of u for y direction you have to consider v, and in z direction you have to consider w. Okay, so now if I consider that we have finite number of inlets and outlets and I have one dimensional flow, so then ultimately this integral term I can write in the form of summation term. Okay, so how I can write then that my f vector will be nothing but equal to integral over the control volume del by del t v vector rho dv bar plus, in place of integral now I will be writing summation, then what I can write, v vector rho times v vector dot n cap into a. Now I can simply write a because I have also taken the assumption of 1D flow also. Okay, so simply a, and I will put some subscript I over here. Okay, so still in this summation I am having both inlets as well as the outlets. Why? Because this v dot n I am considering. Okay, so for outlet it will be positive and for inlet it will be negative. Now if I replace this v dot n with normal component of the velocity only, in that case what I can write? I can write that f vector will be nothing but integral over the control volume del by del t v vector rho dv bar plus summation of v vector rho vna. Okay, and this whole I for the out minus summation v vector rho vna, this is also I, and this whole is for the inlet. Fine. So if in place of the vector, if I consider only the component normal to the area, then my sign will not be coming into the picture. So that's why outlet and inlet I have to write separately. Okay. Now if you see this term rho vn into a, what is this? Mass flow rate. m dot. Here also it is nothing but mass flow rate m dot. So from here, ultimately, I will be getting my equation that F vector is nothing but equal to CV del y del t V vector rho dV bar plus summation of m dot into V vector I for out minus summation in m dot into V vector I. This point is clear. So it means that the net force acting on a fluid element is nothing but equal to the rate of change of linear momentum of the control volume plus net change of linear momentum across the boundaries of the control volume. Okay, so first term is net rate of change of linear momentum of the control volume as a whole, as a volume, and this is net outflux of, because out minus in, so net rate of outflux of linear momentum across the boundaries of the control volume. Okay, so if I calculate these two quantities, then ultimately I will be easily able to determine the net force acting on a fluid element. Okay, now how to further simplify this? So if you consider that if you have a steady flow situation, so if you have steady flow situation, then variation with the time will not come into picture. Then ultimately the net force acting on the fluid element will be simply equal to summation of m dot V vector I for outlets minus summation m dot V vector I for inlets. So simply the net rate of outflux of the momentum across the boundaries of the control surface. Okay, so this is one very important equation, and this is very strong equation. Why strong equation? Because majority of the fluid dynamics problem, by just calculating the rate of change of linear momentum only, you can determine what is the total amount of force acting on the fluid element. Okay, and this total will include all the forces like pressure forces, viscous forces, body forces, so all are coming in this F vector depending upon the situation. Okay, so, and if in addition some external force is also acting on the body, that will also be accounted in this. Okay, point is clear? Now typically whenever we will be doing this type of problems, one more thing we will be finding out, that till now we have not seen in very detail how to find the viscous force. Body force we know very easy, so it's nothing but mass times g, but one more force can come into picture, that is pressure force. Okay, so let's first talk about that how to estimate the pressure force acting on a fluid element. Already I have given you the idea for infinitesimally small control volume while we were discussing about the fluid statics, and you know that pressure force acting on a fluid element is nothing but equal to, on per unit volume basis, is nothing but equal to gradient of the minus gradient of the pressure. Okay, so that we have seen. But if we have a finite size control volume, then how we can determine this, that let's try to see. So if I consider that I have a control volume and this is my control surface, so over this control surface, can you tell me how pressure will be acting? So say only this control surface is subjected to atmospheric pressure. Okay, so if it is subjected to atmospheric pressure, I will be finding, we know that pressure force always acts normal to the surface. Okay, so normal to the surface, I will be drawing these arrows, and ultimately I am also saying that what I am saying, that it is only subjected to atmospheric pressure. So if it is subjected to atmospheric pressure, then from every side I will be having actually uniform pressure which is acting on the, so length of arrow I am trying to keep it same. So even if I am not able to, then please understand that this should be same. Okay, arrow should be normal to the control surface, and so this is how pressure is acting on the control surface. Okay, so if I have to find out the amount of force which is acting on this, that will be equal to integral over the control surface pressure times, so pressure is acting in inward direction, and if I see any over the any elemental area dA outward normal vector, that will be something like this. Okay, so minus, because pressure and n cap are in the opposite direction, so I will be writing over here minus n cap times dA. Okay, and ultimately it will be becoming integral minus P. So P is nothing but P atmospheric over here, because I am considering this to be atmospheric pressure. Okay, so minus P atmospheric into n cap and dA. Okay, so this is my pressure force. Fine. Now, can you tell me what is the magnitude of this force?
Sir, again, the direction you have made for the arrows denote the sign of the pressure force, not pressure, right?
Yes, pressure force. So, what I am trying to say over here is that if you consider this F, so this is, can you tell me what will be this magnitude? So if you see, this is nothing but I have a closed curve. Okay, so when I have a closed curve, then what I will be experiencing, if on the closed boundary of a curve uniform pressure is acting from all the directions, then ultimately pressure in two perpendicular projections will be actually cancelling from both the sides. Okay, so if you take its projection in x direction, this side also same pressure is acting, this side also same pressure is acting. If you take vertical projection, this side also same pressure is acting, this side also same pressure is acting. So ultimately this must be equal to 0. So it means that if you have a closely bounded control surface, okay, so this will be only possible if you have a close bounded control surface. Okay, so if you have a close bounded control surface, and over that close bounded control surface, if what we have, if pressure is acting uniformly from all the directions of the control surface, then ultimately the force because of pressure on that will be equal to 0. Fine. Now, another important conclusion also I can make from here, if I apply Gauss divergence theorem over here, then what will be this quantity? If I apply Gauss divergence theorem, so this is area integral. This area integral can be converted into volume integral. Line also, volume also. Okay, so if line you have to convert, then you have to go for Stokes theorem. But if you have to convert into volume integral from the vector calculus, then we have to go into the Gauss divergence theorem. So if I apply Gauss divergence theorem, then I can write it as minus volume integral gradient of PA times dV bar. Okay, so ultimately what I can say, I can also say that this force I can write completely in the form of volume also for a closed, but condition is that it should be a closed bounded. Okay, so if it is a closed bounded, and of course all the control volumes will be nothing but closed bounded, because we are defining a control volume around a fluid element, so it will be a circle, closed bounded. Okay, so then ultimately this force in terms of volume can be written as gradient of PA times dV bar. Point is clear? So ultimately I can say that if I write this particular formulation of the force, then I can say that it is not even depending upon the shape of the control volume, because area is defined by the shape. Okay, so it is not having much role on the control surface also. Okay, now let's come to the real situation. Always a fluid element will not be subjected to uniform pressure. There will be some non-uniformity. Okay, so if I go to the real situation, then I may have that the uniform pressure is PA. So let me draw a similar spectrum again. This is the PA pressure which is acting, but this is not only the pressure. Say we have certain more pressure also acting in certain portions, not everywhere but in certain portions. So say here I have some pressure P acting over here, and this inside pressure is PA. Okay, so now this is not acting everywhere but in only certain portions. So now you tell me, do I have the uniform pressure at all the sides? No. If I don't have uniform pressure at all the sides, so ultimately this will give me some net resultant force acting on this control volume because of the pressure force. Okay. So ultimately, if I see the uniform pressure across this is PA. Okay. So whenever I will be computing the component of the force, the contribution of PA will be cancelling out. The net pressure which is acting on this will be nothing but P minus PA, but only on this area, and here also P minus PA, but only on this particular portion. Okay. So ultimately, if I have to write down the force because of the pressure, then I will be writing integral over the control surface, but not the entire control surface, only the portions of the control surface where I have, okay, I can write it entire also, no problem. But now what I will do, in place of the pressure, I will write now P minus P there. Because PA is acting uniformly in all the directions, so its effect will be cancelled. So ultimately the net pressure which will be causing force, that will be nothing but equal to P minus PA. Okay, and minus n cap times d. So now if I take even the integral over the entire control surface, in these portions P minus PA will be 0, and only in this portion and in this portion P minus PA will be having some magnitude. Okay, so ultimately I can say that the pressure force acting on a fluid element will be equal to minus of integration of the control surface. This P minus PA I can write as P gauge. On a gauge scale it will be P gauge. So gauge pressure acting on the boundaries of the control surface times n cap d. Point is clear? So this is the net force which is acting because of the pressure. I must put a vector over here because I am using n cap, which is a vector quantity, so I must put a vector over here. Okay. So this is how I can easily estimate the pressure force. Body force we already know, pressure force we have seen. Now one more force will be coming into picture, that is the viscous force, but that we will talk subsequent in subsequent lectures. Okay. Okay, now anyone is having any doubt in this point? All are fine with this what we have discussed? Now let's try to see some of the numerical problems related to these concepts. Okay. So first problem we have is, we have a tank which is shown in the figure, and this is being filled with water by two one-dimensional inlets. So the once we heard the word one-dimensional, it means that over the entire area of the inlet, density, velocity, any property is actually uniform. Okay, it is uniform. It is not varying over the inlet. Okay, so we have two one-dimensional inlets. Air is trapped at the top of the tank. So this is a sealed tank, closely sealed tank, and air is trapped at the top of the tank. The water height is h. So at any instant, whatever the water height is there within the tank, that is h, and we have to find an expression for the change in water height dh by dt, and we have to also compute dh by dt if d1 equal to 1, d2 equal to 3 inches. So these two are in inches, and velocity through inlet 1 is 3 feet per second, velocity through inlet 2 is 2 feet per second, and area of the tank is actually 2 feet square. And we have to assume water at 20 degrees Celsius. So if I am assuming water at 20 degrees Celsius, then ultimately I can actually compute the density of the water. Okay, fine. So can you tell me how to solve this problem? What we have to do now? How I can solve this? First tell me, do I need to apply the conservation of mass principle over here, or do I need to calculate the rate of change of linear momentum for this? Please tell me.
So we can first calculate the rate of change in the momentum, then we will get the force by which the air is compressing.
Okay.
And
Do we really need force in this case? We have to simply quantify the height. What happens if you have a tank? You consider your tank at home, okay, and this tank is connected to two inlets. So if water is coming say at 5 lpm from one inlet, at 7 lpm from other inlet, then ultimately at what rate height will be rising? This is a simple question, even I need not to do analysis. Area of the tank is constant. So I will be saying total flow rate into the tank is 12 lpm, okay, and that must be equal to, because that 12 lpm is actually changing the volume, that must be equal to change in volume of the water divided by time. Change in volume of water is area into height by time. Okay, so simply I need to apply over here the conservation of mass. Okay, so how to apply conservation of mass point by point, let's understand this. Okay, so first point is, we know that as per Reynolds transport theorem, d by dt integral of rho dv bar plus summation of, tell me, summation of v vector rho, or if I consider one dimensional inlet, then rho v into a I out minus summation v rho a I in equal to 0. Okay, so now it is given in the question that both the inlets are actually, both openings are nothing but inlets. Okay, so as both openings are inlets, so my outlet term has already become 0. Point is clear? Outlet term has already become 0. So now I need to quantify this and this. So how to quantify this? I can write over here d by dt integral rho dv. Okay, so what is the present height of water in the tank? Present height of water in the tank is h. Rho w is density of water, at is area of tank. So presently mass of water in the tank is how much? Rho w at into h. This is the mass of water in the tank. Okay, so rate of change of mass of water, what is integral rho dv? Integral rho dv is nothing but mass. Fine, so mass I have calculated over here, and I have to do d by dt of this. So d by dt of rho w at h. Is this one clear? Now till now I have not considered the total mass. I have only considered the mass of the water. Now I need to consider the mass of the air. So can you tell me what will be mass of air over here? What will be mass of air? Rho air, area of tank, into what is height? This is the mass of the air. Fine. So plus d by dt of rho air at into h minus h. So this is now the first term is completed. First term is completed. Okay. Now this term is already 0 minus what is rho avi? So it will be rho av1 minus rho av2. Okay, rho av1 minus rho av2, and this ultimately will be equal to 0. Why 1 and 2? Because 1 and 2 are the two inlets, okay, which are connected to the tank. Okay, now tell me, when I will be finding that water is getting filled inside, the height of the water will rise. So if height of water is rising, then mass of the water is actually changing. Okay, but if you consider the top of the tank is actually perfectly sealed. So if you consider, though my H minus H is decreasing, but when H minus H is decreasing, air cannot go out of the system, air is getting compressed. So if air is getting compressed, the rate at which H minus H is decreasing, at the same rate density of the air is also increasing, and ultimately whatever the quantity of air is enclosed within this tank, that is remaining the same. Okay, so if mass of the air is remaining same within the tank, then ultimately my this term will be equal to, what will be this term? Can I say this to be 0? Because this entire quantity is nothing but mass of the air, whatever quantity is inside the bracket. Okay, and because tank is perfectly sealed, air cannot go out of the tank, so mass of the air is actually not changing with time. Point is clear? Anyone is having any doubt? So if mass of air is not changing with time, then ultimately this will be equal to 0. Now here if you consider area of tank is constant, density of water is constant. Okay, because pressure, you may say that air is getting compressed, so pressure is changing, but pressure has very minimal effect on the density of the liquid. On contrary, the parameter which changes the density of the liquid, that is temperature, that is given constant. Okay, so that way I can say that rho W and AT are constants, so this will be equal to dH by dt. And our first part is nothing but we have to calculate dH by dt. Okay, so this is equal to, this is minus rho 1 A1 V1 minus rho 2 A2 V2 equal to 0. Now water temperature is given same for everything, for water present in the tank as well as for water coming through the inlets. So ultimately I can say that rho 1 will be equal to rho 2 will be equal to rho W. So density will be same. Okay, so if density is same, then ultimately I will be getting AT times dH by dt is nothing but equal to A1 V1 plus A2 V2. What is A1 V1 plus A2 V2? So this implies dH by dt. If I say Q as the volumetric flow rate, then I can write this as Q1 plus Q2 by AT. So this is my part A. Fine. All are fine with this? Now what is the second part? The second part is we have to just substitute these values and calculate dH by dt. So this numerically you can calculate by your own. So I am not going to do the second part because the main portion we have done. Now you can substitute values and find. Fine? Yes?
Sir, initially this we use for conservation of mass equation.
Sorry? Where?
Sir, this one. So the first equation, on what basis have we used this equation?
I have considered a fixed control volume in space which is having finite number of inlets and outlets, and inlets are one dimensional.
So, sir, it is equal to rate of change of the property.
Rate of change of mass.
Rate of, but so the mass is changing, but we have put it equal to 0.
Mass of the system, dm system. Recall the Reynolds transport theorem. Okay, what we do? As per Reynolds transport theorem, this entire quantity is nothing but equal to
dm by
dm system by dt. Okay, and m system by dt is nothing but equal to 0. That is the application of the Reynolds transport theorem, that anything which we know for a system, that we are converting into the control volume.
Sir, in this case, how is it 0?
What?
Means rate of change of mass of the system.
Rate of change of?
dm system by dt, how is it 0 in this?
What you have to do, so that is the difference over here. Whenever I am talking about dm system by dt, I am considering the control mass approach. Okay, so in control mass approach, nothing can enter across the boundaries of the control volume. Closed system approach in thermodynamics. Okay, how system approach is getting converted into control volume approach, that is something which we have studied through the Reynolds transport theorem. So ultimately what is happening over here, let me tell you. If you consider this as your system, okay, so then whenever this fresh fluid is entering, then your system is being displaced in the top direction. Okay, but this displacement of, while this displacement of the system is happening, if I consider a control volume, then I say that this portion is added, removed from the control volume, this portion is added in the control volume. So ultimately that helps us to convert it into the control volume approach. Okay, so don't try to put a closed mass over here now, because what we have done already by taking the help of the Reynolds transport theorem, we have converted the formulations which are applicable for a mass into a, for a closed mass, that to a control volume. Fine. So what I am trying to say over here is ultimately that dm system by dt equal to 0 for a closed system, and for a control volume this entire quantity can be written like this, and so that must also be equal. Okay. Okay, problem number 2. So some figure is given, and as per this figure we have a fixed vane. So this is a fixed vane, so it means this vane is actually fixed in space. Okay, and a water jet of area A. So from here the area of the water jet is A, through an angle theta. Vane turns a water jet of area A through an angle theta. So you can see a water jet is coming over this vane and then it is turning at an angle theta. Okay, initially this was the direction of motion of water jet, now this is the direction of motion of water jet, but this has been deflected by this vane, so it has deflected through angle theta now. Okay, by changing its velocity magnitude. Okay, so while it is deflecting, it is saying that without changing its velocity magnitude. So it means when this vane is actually deflecting it, velocity at this point and at this point at both places are same. Okay, the flow is steady, it is not changing with time. Pressure is PA everywhere. Okay, so it means that force because of the pressure will be 0. Okay, and friction on the vane is negligible. If friction on the vane is negligible, there will not be any viscous dissipation. Okay, find the components F and Fx and Fy of the applied vane force. So F, from here, if we are subjecting some force F on the vane, okay, so we have to find its components Fx and Fy, and we have to also find the expression for the force magnitude F and the angle phi between F and the horizontal. Okay, and we have to plot them as function of theta. So phi, we are considering that some angle which is made by this force with the horizontal. So that angle is phi. Okay, can you tell me what I have to do over here? How to solve this problem? How to solve this problem? Already a hint is given in the question. They have already put a control volume around it. Okay, so already a control volume is enclosed around our system of interest, zone of interest, region of interest. Okay, so how to solve it? Please tell me now. Remember one thing, we have to calculate force. What is force? Rate of change of linear momentum. Okay, so if I consider the rate of change of linear momentum equal to force, first, and of course this force is having two components. One component will be fx, other component will be fy. Okay, so I must write that f vector, today only I have given you this equation, f vector will be equal to d by dt of integral over the control volume v vector rho dv bar plus summation mi v vector I for outlet minus m dot I into v vector I for inlet. So that is my force. Okay, now this force I can also write it in the component form. Already I have told you, in the component form we have to consider velocities in individual directions. Okay, first thing is, it is given in the question that we have a steady state situation. So if we have steady state situation, this whole term is equal to 0. This whole term is equal to 0. Understand? Now, if I consider the total force in x direction, total force in x direction will be equal to mass flow rate out in x direction into velocity of this in x direction, vx out. Okay, summation of this, if I have multiple inlets and outlets, minus inlet mass flow into component of velocity at inlet. Fine. Up to this point, is it clear? Now go back to the question. So if you see, what is the inlet velocity in x direction? So if I fix my coordinate frame like this, oh, already it is given. So this is the coordinate frame, it is given x and y. So what is inlet velocity? Vx inlet is nothing but equal to v. And what is outlet velocity in x direction? So this is the v vector having angle theta. So I can simply say that Vx out will be nothing but equal to v into cos theta. Fine. Similarly, let's also try to see the velocities in y direction. So what is y velocity at inlet? Y velocity, because entire velocity is in x direction, so y velocity at inlet is equal to 0. What is y velocity at outlet? Y velocity at outlet is equal to v sin theta. Okay, now let's try to see these. So ultimately what I will be getting now, that sum of forces in x direction will be equal to m dot out into Vx out is v cos theta minus m dot in into Vx in is equal to v. Okay. Now one more thing. This jet is only deflecting. So ultimately the mass which is at the inlet, same will be mass at the outlet. Okay, mass flow rate will be same at the inlet and the outlet, because area of jet is not changing, it is only deflecting. So what I can say is that as per the given situation in the question, m dot in will be equal to m dot out, which will be equal to m dot. Okay, so ultimately I can say that sum of forces in x direction is equal to m dot v times cos theta minus 1. All are fine with this? Now what will be summation of fx? Summation of fx will be sum of all the forces which are acting on this. Okay, so what are the forces acting on this? I can consider pressure force in x direction. I can consider viscous force in x direction. Okay, and I can consider, already it is given in the question, you see, this F vector because of the vane is actually acting on the fluid. So if this is acting on the fluid element, so this will also give some external force Fx over here, and this Fx is actually in which direction? Okay, I can consider in any direction. Let me consider in positive over here at the moment. Okay, so I have plus some force which is acting because of the vane. Okay, now F viscous and F pressure will be equal to 0. So only the force which is acting because of the vane, that becomes Fx equal to m dot v. Let me use this summation of F Rx. Rx means I can say the resultant or total force, or let me write Tx means total forces, because it is getting confused later on with this Fx. Okay, so that's why I am writing over here total force Ftx. So Fx has become m dot v cos theta minus 1. Another assumption which we have made over here is that we have considered that weight of the jet is actually weight of the control volume is negligible. If we are considering weight of control volume, then ultimately we must add over here the body force also, but ultimately body force will not come into x direction, that will come in vertical y direction. So that's why I have not written over here actually. Otherwise I could have written plus body force and then neglected that as well. Fine. Point is clear? Okay. What about y force? So total forces in y direction will be equal to m dot out into vy out minus m dot in into vy in. So ultimately, as I told you, we are neglecting many forces. So only force because of the vane which I will be considering, that will be Fy. So Fy will be equal to m dot, again I can take common, but I need not to, because V out is becoming V sin theta and inlet is 0. There is no inlet component of the momentum in y direction. Okay. So ultimately my net force F will be becoming how much? Fx square plus Fy square into square root. Okay. And if I have to find out the angle at which this force is acting, so angle will be nothing but tan inverse Fy by Fx. That will be the angle at which it will be acting. And if you calculate this angle, it will comes out to be theta by 2. Okay. So if you calculate phi equal to tan inverse Fy by Fx, it comes out to be theta by 2. Just apply simple trigonometric relations. Okay. So ultimately, the B part of this question was that we have to plot the variation of this net force as function of theta. So say if angle of deflection is changing, then what will be happening? So you can see from here that when I will be calculating the resultant force, that will be becoming m dot v into that can come out common from both the sides, and it will be becoming cos theta minus 1 square plus sine square theta and square root of this. Okay, ultimately you will be finding that it will become a parabolic function of theta. Okay, square of theta will come into picture. So with theta I will be finding variation of force will be, so what you have? You have this resultant force now as function of theta. You can keep on substituting the different values of theta, and you can calculate F by m dot v. Okay, and you can plot this graph, say from any values varying from 0 to 120 degree or 150 degree, whatever is given. Okay, and phi, as I already told you, that resultant has come equal to theta by 2, so that will be a linear line. So this will be line for phi and this will be line for F by mv, and let me consider scale of phi on this side. Okay, fine. Now if you have to visualize it, let me also show you that portion. If you have to visualize it, then how you can visualize? You can visualize the net momentum in x direction is m dot v. The net momentum at an angle theta is m dot v. What will be their vector sum or resultant? This will be their vector sum and resultant. Okay, what I was saying is that it is not allowing me to write. Okay, so I will give you this idea about the vector sum in the next class. Okay.